So yes, for the seminar today, I thought I will tell you a bit of an overview of the activities at Quandela. Of course, I think there will be a bit of a bias towards what the theory and software team are doing. I will try also to give some insight into the hardware and into our roadmap. But I'm also not myself an experimentalist, so don't expect like a very strong level of detail on that. So about Quandela, so it's now I don't know if it even can be called a startup because we are already more than 100 people. But it was founded in 2017. Initially, it was a spin-off from the group of Pascal Senla at C2N. Yeah, it has grown a lot since. So still like the main offices and the labs there in Massy and in Palaiseau, like in the south of Paris. But we also have some offices in different countries, including a branch, for example, in Canada. And we're also, I think, expanding to South Korea, for example.
And are you going to expand to Poland, maybe, in the near future?
I don't know of any such plans. I know there is for sure an office in Munich, and
Okay.
I think
But
there are
it's still not
also
Poland.
definitely like collaborations with groups in Poland, but I don't know about opening an office. We'll have to see.
Okay.
So there's quite a few photonic quantum computing companies that exist. So I think the most famous one is PsiQuantum. There is also Xanadu, Quix, and Orca, for example. And I just wanted also to clarify that the type of photonics that we are doing at Quandela is not continuous variable. So we're doing like discrete variable photonic quantum computing. So I just wanted to clarify because sometimes we often get questions that are more related to like CV stuff. So it won't be covered here. So yeah, I will tell you a bit about the experimental setup for the kind of devices that we are doing now. So it's spoiler, it's using linear optics. So then I will talk a bit about linear optical quantum computing. I will give some examples of the algorithms that we are developing on these near-term devices. And then I will tell you a bit about what's next, what's our roadmap to fault tolerance. So the kind of processors that we are building at the moment, they are basically always following the same schema as the one that we presented in this paper, a versatile seed and photon-based quantum computing platform. So that one was for like using a chip like with 12 modes and 6 photons, but now we are like also scaling up like in the size of the chips and number of photons that we are controlling. But basically like the first element is a single photon source. And then we have like the setup that continues. And so I wanted to start a bit by talking about this first element, like the single photon source. So what are the properties that we are interested in a single photon source? Well, so if we look at this picture here, we imagine that this is our source and those are our photons. So this is actually more of the properties that we don't want, like let's say. So we want to be able to, every time that we use the source, we want to emit one photon. So that would be like single photon purity. We don't want to emit, for example, like 3 or 2 photons at the same time. We want the source to be kind of on demand, so to have like very high, what we call brightness. So whenever we like somehow use the source, like we action the source, we want to be able to produce a photon. And we also want the photons to have similar properties. So that would be indistinguishability. So here I chose like different colors to show that those would be like distinguishable. So that the ideal single photon source is working on demand, has very high single photon purity and very high indistinguishability of the photons that it produces. So the kind of sources that we use at Quandela, which is actually the sort of technology that was initially at the heart of the company, are quantum dots. So they are kind of artificial atoms that you can make in semiconducting materials. So here it's actually in like gallium arsenide. And so you basically have like a place where you have some very, like in space, like this sort of like little box, let's say like this quantum dot, where you have like some very specific energy levels that are defined. And when you shine a laser onto the quantum dot, you can excite an electron into a higher energy level. And then when it goes down, when it recombines with the hole, it emits one photon. And that happens kind of deterministically, totally deterministically. So the only thing is that it can be emitted in kind of any direction. So that's the part which is more difficult. So you could have like the emission that are going in any direction. So that's why it's important to place the quantum dots in what we call a micropillar cavity. So you can imagine it's like made of a lot of kind of mirrors that allow you to redirect the photons into one specific direction, and then you can like obtain them all into an optical mode and then onto your setup. So then we can see we continue here in the setup that we have here. We have like the filtering that's for the laser light actually to be filtered. And then the photons go into the demultiplexer. So the reason why we have a demultiplexer is because we are working with one source, but we want to be able to send several single photons kind of at the same time on the chip. So we need to be able to transform like a train of single photons into like single photons kind of in parallel sent to different optical modes. So this is done by having like basically like some delays, like some loops in which some of the photons are waiting for the others. It's actually, I think in an engineering point of view, it's quite a component that requires like a lot of work.
So how you delay this photons? What do you use for that?
I think just basically like you keep them like in cables for like a really long time until the next one arrives. A really long time. I mean, it's very short, but like the cable has to be long because of the speed of light. And so it's like some of them are waiting for the next one. So you need quite just specific controls to do that.
But you use optical fibers for this, or?
Yes, yeah.
But then it's like takes out of place, no? Well, I don't know how it's being.
Yeah, I think in the end it can be like I think quite like it's not huge, but like it does like it's a component, like it's taking some space, yeah. Like it's not much huger than the rest, but yeah. Okay, yeah, and then onto the chip. So for the chip, of course, like it used to be like a lot of setups used to be free space. And here I'm doing also a bit of a self-promotion of our work with Remik from a few years ago when we participated in this work where they had like demonstrations of on-chip photonics. And I think now a lot of things are done on-chip and it's really like, it changed the game in terms of space. So yeah, you were asking about the space that the multiplexer is taking. And of course, like actually the chip is not taking much space at all, whereas before when you had like these huge optical tables, that was much more costly in space. And then after, while going through the chip, so I'll explain a bit more also like what sorts of operations we can make here on this chip. But then we go to the SNSPD detectors, which are made of superconducting material. And so basically the photon arrives here and breaks the superconductivity. And so you have a voltage that you can measure, and that's how you see that you have a photon that arrived on the detectors. And they are quite efficient. I think we have like higher than 95% efficiency in the single photon detection. But one thing which is more challenging is having photon number resolution. So being able to observe a state where you have, for example, in one mode you would have like two photons. It's still challenging to do in practice because these detectors are more like threshold detectors. So I think you can do some things with like, for example, analyzing like the electrical signal that you get and try to understand if you had like one or more photons, but it's still something that's really, I would say, in progress. Okay, so yeah, so that's the whole experimental step. And of course, in order to communicate with the setup, decide like which input state has to be prepared, which operations we want to make, and to be able to save the results, we have a cloud system. So actually like a classical processing unit connected to the lab, and that then sends the results to the cloud. And the interface is all done in Perceval. So I will maybe come back to this actually. Yeah, here. So it's this software that we have been developing for the last few years, and it allows you to do a lot of simulations of linear optics, but also to communicate with the cloud. Yeah, and maybe then something that I wanted to say about noise. So at the beginning, I was talking about the different types of noise that we can have at the source, so like the purity, distinguishability, this sort of stuff. And then, of course, on the setup, the main one is photon loss. So it's the main source of noise, for now, like the biggest one, and also one which appears at kind of every step of the setup. So in here you can see this was for the paper that I was mentioning, like for the Ascala QPU. So yeah, we have some loss that is happening for the detectors in the demultiplexer, in the chip, etc. And so at the time back then, we were able to get a total efficiency of 8%. And I think our near-term target is like overall 27% for these kind of setups. And of course, yeah, you also have bad scaling, exponential scaling with the number of photons in an experiment. So if you want to observe, for example, like 6 photons coincidences, you will of course have that the loss or the transmission is going to be to exponent 6. So it's like also kind of making it more challenging to get like a lot of n photon coincidences. Okay. So this I said. Yeah, and for the cloud, so yeah, I was telling you, like with Perceval, you can prepare the input state, tell which circuit you want to do. You also have like important points about the compilation and transpilation process. So the compilation is transforming the unitary that you want to give to your chip to the actual phases that you need to tune. And then transpilation is like deciding like in order to implement these phases, what are the voltages that you're actually going to apply to the phase shifters and beam splitters in the chip. And in this part, we have actually an interesting process that is some of my colleagues have worked on this to compensate for the sort of thermal crosstalk that we can observe. So because when you're applying the voltage, you can of course kind of contaminate, let's say, the phases that are close by because everything is like so close in space. So we have some mitigation processes to compensate for that. Okay, so I think that's it. I don't know if there are more questions
So
on.
I would have one.
Yeah.
So what is this Ascala?
Yes.
Okay.
So I mentioned Ascala was like the. Oops, maybe I go back to the slide on which I was. Yes, showing the. I think it's that one. Yeah, it's just the name that we gave to the QPU that we had presented in this article. So by QPU, I mean quantum processing units, and it was the one that had like 12 modes and 6 photons. It's just the name that we gave it. And now, for example, the one that we are going to release now, it's going to be called Belenos, and I think we can go up to 10 photons in 24 modes.
Okay.
Can I ask you one question? Sorry.
Yeah, of course.
Hear me? So, what do you mean? I am not any kind of expertise in this field, so let me ask you a very silly question, maybe. So, what do you mean by a single photon quantum computing? Yeah, I think in your presentation it uses multi-partite photons, but is it a single photon anyway? Sorry.
Yeah, no, it's a good point. It's so of course, yeah, and especially when I was saying, for example, that we when I was talking about like the coincidences, etc. So by single photon, I mean that somehow like the particles that we are controlling, it's always like one single photon instead of being like I don't know, when you think about like classical light or laser light, there would be like a lot of photons. So here we are able to control the photons somehow, but one by one by emitting always one and like being able to use it to encode information.
I see.
But of course, you will have to prepare like states with several single photons because otherwise it won't be interesting. Like if you want to make something with entanglement, you will have entanglement between 2 single photons, for example.
I see. So controlling single photons. Okay, I got it. Thank you. Thank you so
Sorry,
much.
so may I continue because this confuses me a little. So is there a concept of 2-qubit quantum gates, like for instance, in this setup?
Well, we will come to it. Like, what is a qubit exactly? How would you define a qubit? This is
Okay.
your question, right? Yeah,
Okay.
it's actually coming very soon. So good transition for the next section actually on linear optical quantum computing. So yeah, I wanted to clarify what do we mean by linear optics, and in particular, I think sometimes it's also referred to as passive linear optics. So yeah, it's also referred to as like discrete variable linear optical quantum computing. So the idea is that we have a photon source, some detectors, some modes, and we can use like beam splitters and phase shifters on an input of single photons to perform quantum computing. So you're using phase shifters and beam splitters to do your operations. And the sort of states that we are starting with, they're like Fock states. So they're usually like describing the number occupancy of each mode. So it's telling you, okay, in like mode 1, I have N1 photons, so here 1. In the second mode, I have 0. So this would be like, for example, your input Fock state. This is how you would describe the state that you see here. And the output Fock states after all of the operations. So this here you see that you have like 2 photons in the second mode. So this is like how we denote the states that we work with in linear optics. So still at this point, still not qubits, but it will come. So I was saying that the operations are made by beam splitters and phase shifters. So yeah, like we are talking about like linear optical transformations on M modes that are belonging like to U of M. And the beam splitters are U2 transformations and the phase shifters are U1 transformations. So the beam splitter acting like on 2 modes and the phase shifters just on 1 mode. And they look like this. And then there are some interesting decompositions. So if you want to decompose any like unitary matrix in the space M by M, there exists like M mode linear optical circuit that can implement it. So this was first proven by Reck and co-authors, and then optimized even later by Clements and co-authors. So this is the Reck scheme. So it's telling you like how you have to arrange all of the beam splitters and phase shifters in order to be able to do like any of these unitary transformations. And then the Clements scheme is a bit more compact, which is better in terms of losses, because like somehow the shorter your circuit is, like the fewer photons you will lose. Okay, so, but okay, here it's important to know that we are like talking about any unitary in this M by M space, so it doesn't correspond to any unitary in the Fock space. So that's also a bit of a subtlety. And so it's using linear optics that the problem of boson sampling was defined. So this was introduced by Aronson and Arkhipov in 2011. So you have exactly this setup with like your unitary, your Fock state at the input, you have your detectors. And so the probability of observing a certain state can be actually expressed as the permanent of a submatrix of the matrix U. And the permanent, as a reminder, it's like very similar to the determinant of a matrix, but with plus signs everywhere instead of having like sometimes the minus signs. And then it's like quite hard to compute classically. So the best classical algorithm scale as 2 to the n. And so then based on this information, Aronson and Arkhipov proposed the boson sampling task as sampling from the output probability distribution of such a linear optical circuit. So you need to sample outputs S from like this setup. And they showed that, or like conjecture, I guess it's kind of a proof that it's hard to do classically if you believe some widely believed complexity theory conjectures. So it allows you to have then some near-term demonstration of quantum advantage because it's kind of simple in terms of hardware. Like you don't necessarily have to have like thousands or millions of error-corrected qubits in order to reach quantum advantage. So that's why I think this task also got a lot of attention. But I think one thing which has also like puzzle people is trying to find usefulness for boson sampling, like trying to find like link that task to something that is actually useful or that has an application. So it's also, I think, a challenge that we are working on.
Well, I guess it can be used for computing permanence, right?
Yes. Yeah, I guess that would be something. Yeah, indeed. You could have yeah, okay, that's true. That's actually one of the examples of one of the algorithms that one of my colleagues designed. So yeah, that's true. Well, I guess you also have some algorithms to approximate like permanence that you can use classically, but yeah, indeed, so that's a good point. You do have also, I think, some challenges with the fact that as the setup grows, also like the probabilities, they become quite small, so it becomes a bit like harder to estimate, but yeah, there is that. So yes, this is the original article that I think is very nice if you want to know more. And then there were some demonstrations for like the Gaussian boson sampling, which is for the CV framework, so the continuous variable framework, which were done by Xanadu and I think a university with the group of Jan Weipan. So now we come to answer your question about like how would you define qubits?
Can I have a question concerning
yeah,
the previous
of course.
papers? So how many photons did they use for the experiment?
Actually, I don't know the details. I'm not sure because it's like, yeah, I think I should check. Yeah, okay, I'm sorry about that. But okay, it's like it would be a bit different because of course they are doing like CV, so the way that they encode will be a bit different. So I guess it wouldn't be like speaking per se about like how many photons exactly. Yeah. Okay, yeah. So then going back to how to define qubits. So yeah, so we choose basically an encoding. So you need to choose an encoding in order to define qubits using your Fock states. And I think one that is super common and the one that we are using is dual rail. So the state 0 is going to be when you have a photon in the first mode, and state 1 is going to be when you have a photon in the second mode. So here it's the qubit state, and here it's the Fock state. So yeah, corresponding to that. And then in that context, you can do like 1 qubit gates fairly easily. So for example, you can, here I didn't normalize, but you can do this transformation with a beam splitter. Also to note that other encodings are possible, not just dual rail, but you could use polarization, for example. But the big challenge here is that if you're using, strictly speaking, just passive linear optics, there are some gates that you cannot do deterministically. And in particular, important gates to create entanglement like C0s or CZs, for example, they cannot be done deterministically natively in linear optics. So there are some options. So one would be to introduce some nonlinearities, like actually like change the definition of your setup to go like also have nonlinear optics. But here, I think it's kind of difficult sometimes to find the materials. It's not super easy. You can also do post-selected or heralded gates. So this is an example here on the right of the post-selected CNOT gates by Ralph et al. And here you see, yeah, okay, so you actually like need 2 ancilla modes. So you have 6 modes in total. This is your first qubit, this is your second qubit, and you will need to post-select. So for example, if you're observing states in which you don't have like 1 photon in this mode, in these 2 modes, and 1 photon in these 2 modes, you cannot interpret them as qubits anymore, and so you will have to discard them. And so I think you typically would have probabilities of success of such gates of like 1/9, for example, to do this CNOT. So it makes the computation becomes a bit costly. And then this brings me a bit to like how then do you define algorithms in linear optics? And I think you can sort of see 2 approaches. So the first one is to do qubit or circuit-based algorithms. You just try to compile them in the best way possible using like these post-selected gates or these heralded gates. So you use your dual rail encoding. Here you would have some gates, maybe you do some CNOTs, and then you discard some of the outputs and you keep only the ones that make sense according to your encoding. So I'm saying here, yeah, the example of why you would discard this output is because there is a photon in the ancilla mode, so it doesn't count as an interpretable state in terms of qubits. So here there are some interesting questions like how to compile best. Can you find like different encodings that make it like for a given algorithm? Can you find an encoding that make it as little costly as possible, etc. And then another option is to do something that we started calling photonic native or photon native, and it's just to work in the picture of Fock states of unitaries, basically in the boson sampling picture. So here you are maybe a bit more limited in like the types of algorithms that you can design, but then you don't have any issues about post-selection or probability of success of your protocol. And so I have here a few examples of the algorithms that we've worked on in the group, and if anyone wants to go into more detail into one of them, we can do it at the end. I have also some additional slides. So for example, in the qubit case, we had like demonstration of VQE when we were introducing the quantum processing unit, the Scala one I was mentioning. We also had like an interesting work from some colleagues about clock encoding, so qubit logic on qubits. So using some qubits in order to define like, or using like a different way to define your qubits so that you can end up with like circuits that have a higher probability of success. And so then it allowed to extend the work from the H2 molecule to the LIH and do it in a time that was actually doable on the QPU in terms of like probability of success, making it like somehow doable in a few hours instead of in a really long time.
Alexia, can you please say more about this
about this clock?
compression? Yes,
Yeah.
about the second paper. So like on the second plot, you have qubit, and then it says for more than 4 years, right, to compute something.
Yes.
And then there is this QLOQ. So this
Yes.
is this compression, right?
Yeah, it's like, so basically if you wanted to do the circuit to do the VQ for the LIH molecule, like let's say the gates that it requires you to do, if you do it like naively, just, for example, using this Ralph synod that I was showing, it gives you, if you take into account the sort of rate that we have, let's say transmission rate, like all of the hardware constraints, plus the probability of success given like the gates that you have to do, it would take like 4 years of time on our QPU. But if you use this compiled circuit, like this compilation, then you can do it much faster. So the hours is like given, of course, given the kind of efficiency that we have like at the moment. But of course, the time would be reduced if you had much, if you didn't have photon loss or this sort of stuff.
But that doesn't mean that you, I don't know, compile or compress several qubits onto one qubit or something, and then you perform.
Yeah, actually, I have a slide to explain this a bit better.
Okay.
Yeah, so it's like, yeah, so how does it go? So it's, yeah, basically, I think it's, you are able, if you want to do instead of, so, okay, let me think. This is like to do a synod between like Q0 and Q1, like if you consider, yeah, exactly. So that's it. So you're saying this mode is 0, 0, this mode is 0, 1, this mode is 1, 0, and this mode is 1, 1. So instead of saying that you have one qubit, like this mode is 0, this mode is 1. So you just like sort of define in a different way, like the mapping between the modes and the states. So you're directly defining this. And then your CNOT, then because the action of the CNOT is going to be like to switch when you have like 1, 0 to 1, 1 and switch 1, 1 to 1, 0, then it becomes just this operation, which is like just a swap that you can do by having like your optical modes swap with each other. So it's like kind of a specific case. And so, yeah, exactly. So then I think there are more examples of how like some gates can be more, some gates will be less costly and some gates will be more costly. So it depends a bit, like it doesn't mean that every circuit will be easier to compile, but like some of them you may be able to replace like a CNOT gate by just a swap.
But do you have some, I don't know, program to compile this? I mean, some software that does this?
I'm not sure it's inside Perceval, the software. Yeah, it's a good, I don't think it's integrated, but I think definitely like, I think it was mainly Liam that was like working on this, and he must have like some code to be able to do this more systematically.
Okay, thank you.
Okay, cool. So to go back to here. Yeah, okay. And so then, yeah, those are examples like in the qubit picture or like that we have. And in the photon native, we also have, in the photon native pictures, we also have some examples. So we had like classifier that we implemented, like just basically like you define the classifier using the probabilities that you get from going from one Fock state to the other that you can compute at the end of your circuit.
Alexia, can I have one more question? Sorry.
Yeah, of course.
About this encoding. So does it mean that by doing this encoding, like of qubits into qubits, you can avoid using non-linearities? Because you said that if you would like to implement CNOT, you cannot use linear optics, okay? But as far as I can see, now you use linear optics, but you have to do this encoding, right?
Yes. So it means it's not something general that you couldn't, you cannot, let's say, compile any algorithm or any set of gates into something that will be efficient. But some specific algorithms, you can make them, like for example, if you just have like one CNOT to do, you can do it deterministically because then this thing is linear optics, just swapping.
Yes,
It's
exactly.
non-linearity, and you can just do it with probability of success 1, exactly.
Yes.
But then, of course, things can get more complicated if you have like several CNOTs, or if you have like, then it's a bit of a trade-off, like trying to see with this encoding, will I get a better success probability or not? But if you're looking just at one CNOT gate, if you use that encoding, you're indeed
Okay, I see. Okay,
staying within linear optics. Okay, cool. So yes, so going back here, so we have some examples, for example, of a classifier that we defined, so like a sort of quantum neural network defined like there in Fock space. We also had this work on solving graph problems with single photons and linear optics. So this is a bit connected to when you were saying we can also use boson sampling to compute permanence. And I guess here the idea is to encode somehow a type of graph problems, for example, isomorphism or finding dense subgraphs. You use like the adjacency matrix of the graph, and then it's going to correspond, the problem will correspond to computing the permanent of that adjacency matrix. And so then you can do it using linear optics. So I think, for example, you can, like, I don't know, compare like the permanent of two adjacency matrices to be able to say something about whether graphs are isomorphic or this sort of stuff. We also, some things in which in particular I was working was like demonstrations of generative learning on our QPUs. So we had one for like a QGAN, quantum generative adversarial network, and also one on a quantum circuit born machine, which is just a fancy name for just basically using a quantum circuit as a generative model, where we were also integrating some error mitigation into the experiments. I'm still working on this topic as well, so I also have some work in progress on this. We also had some interesting work on developing a parameter shift rule for photonics. So the parameter shift rule was something which was initially defined I think, yes, and that has been integrated, for example, a lot into Xanadu's software Palinen. And the idea is to compute like the gradient of a loss function that is computed from a quantum circuit. You are computing the value of the quantum circuit for like shifted values of the parameters. So it's pretty cool because then it doesn't require to do something like finite difference in order to compute the gradient, but you can then do like some maybe bigger shift and you have also an exact solution instead of the approximation that you get from finite difference. Yes, and so then we can see that in some cases it allows for like much better convergence. We also had a nice demonstration of reinforcement learning by some colleagues. And we have also some upcoming work on quantum convolution and neural network. Here it's using feed forward, so we are going a bit beyond purely linear optics. And there are also some other groups that are interested in this topic. So I'm mentioning, for example, some other people working on quantum convolutional neural networks with the group of Elham Kashefi, some demonstrations of kernel methods using photonic processors, more reinforcement learning. So I would say there's, in the group of Philip Walter, Fabio Cialino, etc., there's quite a few things going on. And I also wanted to mention, because it's kind of our new product, let's say it's the new software platform, which is very focused on machine learning. So basically it's like allowing you to, inside PyTorch, which is this tool that's used a lot in machine learning, to add a quantum layer. And so that just corresponds to having, to simulating basically what would happen in linear optical circuits. And so inside there is a strong simulation, so computing exactly the probability. So that's based on this loss work, this loss strong simulation backend. So of course, it cannot like scale to a very high number of modes and photons, but it's a nice way to test for like, let's say, small number of modes and photons, what would happen if you put it inside an ML pipeline. So this was something that was used a lot, like in this challenge that we had on like trying to implement some techniques from machine learning using like integrating like these linear optics inside it. So are there some questions or some specific interest in one algorithm or the other that I should go into, or should I continue? Maybe I see it's already 40 past, so maybe I can go on to the roadmap.
Yeah, I would say you can go directly to the roadmap. It seems that there are no questions. Maybe at the end there will be some.
Nice. So yes, I think you're very likely to be familiar with the idea of a fault-tolerant quantum computer and the fact that we have the threshold theorem, which is saying that if you can go below some specific physical error rate, then with quantum error correction, you're going to be able to suppress the logical error rates to arbitrarily low levels. So this was like some work that I think was at the end of 90s, beginning of 2000, like showing that with quantum error correction, if you can get to low enough levels of physical error, so like controlling, being able to control things like, in our case, photon loss, distinguishability, and making them like optimized enough, then you reach the point in which with quantum error correction, you will be able to logically correct your qubits. So for photonic platforms, I think a lot of scaling proposals so far were based on the measurement-based quantum computing picture. So this was first presented in 2001 as a one-way quantum computer. So there the idea is that you prepare a big cluster state and you make measurements on this cluster state in order to do your computation. So you're sort of preparing all of the entanglement and the connections offline in advance, and then you make measurements in order to do your computation and with some small corrections. So it's called one way because like in a way you're like kind of losing parts of your state as the computation advances. So for example, there is the fusion-based quantum computation proposal that was done by PsiQuantum. And it integrates also, like it's something that integrates MBQC into the proposal. And that seems to be like a general path if you want to do like fully photonic quantum computing. So in our case, in order to do something like that, we wanted to show also that we have the ingredients to go towards that. And for example, in the Askela paper that I was mentioning before, we were showing that we can that we are able to generate some small GHZ states, which could then be used like in fusion operations, etc. But I think something which is somehow even cooler and more useful somehow is the fact that we can also generate states where you will have entanglement between several photons that are generated and the source and the quantum dot. So there was actually a proposal which was done by Lindner and Rudolph, where they like explain how you could make like these photonic cluster state strings. So strings because you have like initially a cluster state that is defined like that. So you have like the source and each photon that it's like has emitted, which are all entangled together in like a linear cluster state. And then this was demonstrated by the group of Pascal Senla and also some colleagues from Quandela experimentally already. So, okay, to a limited amount of limited size of the cluster state, but it's like the first ingredient to go towards generating like bigger cluster states. So in this case, you're actually going to have like a magnetic field that is applied to your quantum dot, so that your quantum dot is going to have a spin. And in that case, when you excite the quantum dot, you're going to actually prepare like different sort of excited states according to the spin state in which it was in the first place, in which the quantum dot was in the first place. And so the different states that you're going to prepare are also going to emit photons that will have different properties. And in particular, like for example, here the up state will be associated to emitting right-handed polarization and the down state to a left polarization. So this way you can create like spin photon entanglements. And then you can basically add a few operations, you rewrite your states, you excite again, you emit again, and then this allows you to produce states that, you know, will have, for example, like you have one photon here, and the source. And so you will, here it's an example where you have, so 2 photons and the source that are entangled together. And in principle, if you have like long enough somehow like decoherence time for your spin, you can go on and on until you can reach like a quite large size of the linear cluster state. So this is cool and giving us like some idea of how we could get to the point of creating like these big cluster states for MBQC. But then we also had this very cool idea, and this was at the beginning of our proposal for spin optical quantum computing architecture. So we will be able to do something like FBQC with many quantum dots. But how about using the quantum dots as carriers of quantum information? And also the fact that they can produce photons which are entangled with the quantum dots as a way to make the quantum dots interact together and to be able to make operations on different quantum dots by making the photons that they have produced to interact with each other. So, just to summarize in a couple of sentences, the idea is like now we use the quantum dots as qubits, and we use the photons that are entangled with the spins of the quantum dots in order to perform gates between the quantum dots, so 2 qubit gates between the quantum dots. So we are not like now going from a fully photonic proposal to actually a sort of hybrid matter and photon proposal. So it's indeed hybrid because like the qubits themselves, they are going to be matter, like they're going to be the quantum dots. So so you see you need like an emission process, and then you need to be able to reroute the photons that are entangled with the qubits in order to bring them to some small chips in which you can do some operations. So in order, for example, to do a CZ between the quantum dots. And because these gates that we're doing like on the chip, they're still not deterministic, we have the possibility of just doing them like having like several trials. So every time we ask the different quantum dots to like to emit again photons in case like the Rust gate had not succeeded, and we can try again until it succeeds, and we have managed to create entanglements between the 2 quantum dots. So we studied a bit the different thresholds that we could have for this model. So dependent on our error models that we have. So one is like the Rust gate failure, so the failure of this gate, which depends on photon loss. So because if when you're doing this gate, you lose a photon, you're like losing information basically about your system. Spin coherence time. So of course the spin has to not decohere while you're making the Rust gate. So the decoherence time has to be expressed relative to the time required for the Rust gate. And then the distinguishability of the photons, which will of course have an impact on the quality of the gate that you are making. And we looked at the possibility of using the surface code for the fault-tolerant implementation, and then computed the threshold for joint errors. And so we have here an area in which we would be like below threshold, and we would have fault tolerance. And so to sum up, so the Spark proposal is an alternative to all photonic and all matter-based architecture. It's hybrid. We get similar loss tolerance thresholds to fusion-based photonic proposals. So when we're looking like at photon loss, like the kind of thresholds that we get, they're like similar. And we also have something very cool, which is that we get arbitrary physical connectivity. So this is important because I think a lot of platforms like superconducting qubit, etc., they might, have like some issues with, like, for example, having to do a gate between a qubit that's very far from another one. But here they can be as far as they want because we are making them interact through the photons that they emit. So we have this nice aspect. And the proposal in general is not only limited to quantum dot emitters, so you could also use it to other types of emitters. And there is now a team that's like quite dedicated to scaling, and they are doing also improvement on Spark. So for example, in this more recent work, they're like using it with Floquet codes instead of surface code, and so on. And so maybe to conclude, so in the near term, we are focusing on linear optics, looking at boson sampling, looking at applications and algorithms, error mitigation techniques, this sort of stuff. In the long term, we have clearly the Spock proposal to work towards. And then in the midterm, we actually have some interesting questions on how, let's say, to connect like the near term to the long term. So if we go like from linear optics, we are looking at introducing like some elements that are not from passive linear optics. For example, looking at entangled input states, like what if you do something similar to boson sampling, but with like linear cluster states. Looking at having feed forward, so it's like this measurement adaptivity that you can have inside the circuit. So this was, for example, using this QCNN algorithm developed by my colleagues. And then on the other hand, so that's like going, let's say, using linear optics, but adding elements. And then on the other hand, we're also looking at having like early fault-tolerant models with building blocks from the Spock model. So for example, considering that you have like these, like these spins with the photons and like the sort of operations that you know are not going to be costly in Spock, and what can we do with that? So that's also another way to approach the sort of midterm problem. And so I guess, that's kind of also research direction for now. And in general, we want to find like also more error mitigation strategies that are tailored to photonics. For example, we have some for like photon loss, distinguishability, but we want to go a bit further. We want to improve the compilation and optimization of algorithm. So especially if you're doing like sort of QML stuff, like how do you find like some good strategies so that you can train models at scale. We are also looking for applications and use cases and seeing where we can have like potentially some utility. And of course, as I was saying, we have like an architecture scaling team as well as the experimental teams that are working hard towards Spock, so the Spock model. So that's it.